All right, let's pick up with some selected questions from the second part of the Polar Parametric Test. So we'll just call this Polar Parametric 2. And we'll pick up with number 11. That will be one of my selected problems to go through with you. And number 11 is translating from rectangular form to polar form. So we'll say rectangular to polar. Okay. I'm going to do a little manipulation first to make it easier when I convert. I'm going to go ahead and divide everything or both sides by y. And that will give me something that hopefully we recognize from trig, and that's going to be y equals, and x over y is cotangent of theta. Okay. I'm now going to use my translation. I've already used my translation of cotangent theta equals x over y. I'm now going to use my translation of r sine theta is equal to y. So let's replace this y with an r sine theta. All right, and then we're going to try to get r by itself to complete the equation, and that means I divide by sine theta. And it gives me cotangent theta over sine theta. That's almost in the form that I want it to be in. We'll go ahead and move that sine theta to the top with the identity of 1 over sine theta is equal to cosecant theta. So r equals cotangent theta cosecant theta. Let's go ahead and do number 12 is another sample from that section of translating from rectangular to polar. Number 12 is x squared minus 6x equals negative y squared. All right, we're going to translate that into polar. And I'm going to do a little manipulation first by moving that negative y squared over to the left-hand side. And we should be able to move this one, the negative 6x, over to the right-hand side. All right, so that's going to give me the following equation. Now we can see some translations here. R squared equals x squared plus y squared. So let's just replace this with an r squared. And then, of course, x is equal to r cosine theta. So let's replace this x, 6r cosine theta. And then there's a couple of different ways that I can get to an r equals equation. In this particular case, I'm going to go ahead and divide by r. So divide by r on both sides. And that gives me r equals 6 cosine theta. All right, and if you look back at your basic notes for polar equations, you'll see that this polar equation matches with the original rectangular equation. Okay. All right, let's pick up with number 16. Now we're in the section that says eliminate the t parameter and identify the rectangular equation. So number 16 is the one I'm going to work on with you. All right. We're going to eliminate t. And that's part A, and then part B is to identify the rectangular equation. So identify. So 16 is x equals root 2t, and the equation y equals 4t. And remember that we want to try to do is isolate the t in the x equation if we can. We don't always have to do that, depends on what's easier. And then plug it into the y equation to eliminate the t parameter. So if I'm just writing a rectangular equation, that's all I'm going to do. So getting t by itself means square both sides. And then divide by 2. So x squared over 2 is equal to t. And now we're going to substitute that into the second equation. So y equals 4 times x squared over 2. And I'm going to reduce here to give me y equals x squared. And of course, that's going to be a parabola, specifically a parabola opening up. Okay. All right, let's go ahead and do number 17. That one is going to be kind of a tricky one because of sine and cosine. We're just going to do it a slightly different way. Again, we are eliminating the t parameter, which means that we're going to be writing a rectangular equation. So x equals 2 cosine t and y equals sine t. All right. And remember, we want to try to put this into the form of sine squared plus cosine squared. Thetas and t's are interchangeable, so we'll just go ahead and do that. Okay. Which means we want to isolate cosine, isolate sine. Sine's already isolated. Square both sides, and then that will give me expressions for sine squared and cosine squared. So let's go ahead and get cosine by itself. X over 2 equals cosine t, and of course, this one is already isolated for sine t. We're going to square both sides in order to get a cosine squared and a sine squared to fit this Pythagorean form. And that's going to give me x squared over 4 is equal to cosine squared t, and y squared equals sine squared t. All right, now that I know that, I can go ahead and plug these expressions, x squared over 4 into cosine squared, and y squared into sine squared. So we'll go ahead and do that now. We'll go ahead and put this one first. It doesn't really matter which one goes first. So x squared over 4 plus y squared is equal to 1. That's what we get when we substitute these immediately into our Pythagorean identity. And then if I put a 1 underneath this one, I can identify that as an ellipse. Okay. All right, let's talk a little bit about 19 through 28. All of those were things that you either could have converted like you did problems 7 through 10, which we're going to do with number 25 in just a moment, or convert into rectangular form, or you could have memorized the specific type of polar graph that it represented. So for number 20, it was a rose curve. This was your equation. That was simply a matter of recognizing what you memorized. Limousin with an inner loop for number 23. This was your equation. Again, memorization, and then the relationship of 2 to 3 is what told you it was an inner loop, or had an inner loop. And then lemniscate was r squared equals for number 28. So these were memorized values. Anything that you could add to it in the way of description, I gave you more points for that. Okay, so number 25, let's take a look at. This is a converting one. Like I said, everything else in that section of 19 through 28, you could have converted just like problem 7 through 10. So this is an exception to their general rule. We're going to go ahead and find the positions on the unit circle where the cosine of theta is positive root 2 over 2. And that occurs in these positions. And that's at pi over 4, or 45 degrees, and negative pi over 4, or 7 pi over 4, however you want to say that. All right, so there's the two positions where your cosine value is a positive root 2 over 2, okay? And if we start from the center and we create rays that go through those positions, we end up with an absolute value opening to the right. So absolute value opening to the right. And that's it. All right, just as a resource for the last few questions, I think we're looking at 19 through 28. We said that numbers 20, 23, and 28 were all special polar graphs. And this is the page where we found that information. Those equations occur here for Limousin's. Here's your relationships of A and B. Rose curves, those formulas occur here. Okay, here's some information about the relationships. And then for lemniscates, you had these equations, okay? And the distance or length of the petal and or the circle was the value of A. Okay, just as a resource.